we're live. Okay, well, I did it again. I was accepting a whole bunch of tourist contracts to build up some funds, and I, by mistake, accepted another satellite contract. And this one's for a high polar orbit. But we can do this. Not hard. Specifically, it's at 14 million meters apoapsis and 13.6 million meters periapsis, inclination 90 degrees. Polar. And it's got a longitudinally ascending node, and again, it didn't specify the argument of periapsis, so I'm guessing that just like the other one, it won't matter where we put our periapsis and apoapsis. But this means that we want to change our launch a bit. Well, first of all, we have to build a new ship because this one has to have a mystery goo in it. So we're going to have to add a mystery goo. It's a long way away, so I'm going to put on a higher powered antenna. And that means it's a heavier craft. It's a heavy craft and it's a much higher altitude. So a little bit of reconfiguration, and we have now the B variant of the satellite launcher. Let's go take a look at it real quick. Boop. So here it is. I made it longer and longer until I had enough delta V, and then I thought, wait a minute, why am I doing this? So I strapped a couple boosters on the side and got it short again. So many more stages. Let's open this up. So the decoupler. Okay, so there's our satellite. And you can see that in here we've retained our fixed little antenna, which I'm not sure what the range is on that. It could be that antenna ranges don't matter. I need to learn a little more about that. But we have a high gain antenna, and the orbit that we're going to is way the heck out there. It's out beyond the orbit of Mun. So I'm strapping that on the side, and when we get up onto orbit, that will swing out and activate, and we'll be able to have a connection back to KSP, the KSC Science Center. And there's our mystery goo container that we're supposed to take up with us. Once we get up there, I'll actually run the science and send the science back using the high gain antenna just to verify we can do that. We'll have to do that by hand. I don't have enough custom action stuff set up in the VAB to be able to do that. The way that I set up deployment of the antenna, I want that to be automatic, is if you turn on the lights, it activates. And we did that by going here, and I said lights, and I clicked on the antenna, and it said, oh, there we go, extend antenna. So I hit the extend antenna and put it over into the group actions. We do have custom actions 1, 2, 3, 4 down here, but I don't see. See, if we have one of the action groups up here, we've got all these things we can do. But I don't think we have custom actions properly opened yet, so I'm not even sure why it's showing me custom 1, 2, 3, and 4. Maybe they're, oh, okay, 1, 2, 3, and 4, there are some specific things we can do. That's probably just kind of a, oh, wait a minute. Oh, those are custom access groups. There's my custom 1. Okay, so I actually have action group 1 through 10. Can I? Okay, so in theory, I could map action groups 1 through 10 to things. I didn't think I had that open yet. Maybe there's more to the custom action groups. I opened up the basic action groups, and I thought this was custom. So we've got this. But for now, activating the lights will extend the antenna, and that's in the script. See other changes. We added the SRBs, so we're going to burn the SRBs for a total of 1,058 meters per second, which will get us up through the P-soupiest part of the atmosphere. And then we have this engine, which is a LVT-30. Let's see, is it LVT-30? It's a LVT-30 Reliant. So that's a decent fixed mount engine for operation within atmosphere. And that one will get us another 2,000 meters per second or so, maybe a little more, up to 2,300 if we're nearing vacuum when it's firing. Between those, we ought to be able to get circularized, or maybe almost circularized. Now, the next engine will definitely be in its vacuum delta V. So we've got 1,400 delta V from the next engine up, which is this guy here. And he is a Terrier. And the Terrier is a really nice little space engine. Notice it's 4 times as efficient in vacuum as atmosphere. And that gets us 1,500, which is enough to finish circularization and probably get us, get our apoapsis pushed out near where it needs to be. I am not sure. I did the math on that and then forgot it. Certainly, it's easy enough to do the math. You just plug in V's Viva a couple times and you're done, right? Anyway, the final stage is this engine, which is attached to the satellite. And once we get to it, it will have 1,500 meters per second. Now, when we're maneuvering way out from Kerbin, that 1,500 meters a second goes a long, long way. So I anticipate that we will have quite a bit of fuel left once we get on station. We're not going to try to do any station keeping. We aren't being asked to put this in a Kerbal synchronous orbit or anything. We're just being asked to match an orbit. The other thing that I've done, which is different from the A version, is there's a separator right there. So this is the engine plate that I'm using to get a shroud over my satellite. And I put a separator on there, so when we are done with the stuff below the engine plate itself will, here it is, will separate, which will cause everything below it to fall off. We'll still have the plate and the nose cone on there. I worry that we might end up in an attitude where all of the solar panels are shadowed because we happen to be pointed directly at the sun. That would be bad. It would be especially bad if we were stable in that attitude and we never got out of it because we would lose control and all that. So I added the separator there. And those arrows pointed down. Normally your separator's arrows point up because they separate it into them and the stuff below them and the stuff above them, and they go away. So it's the stuff it points from goes away. So the nose cone will go away, the plate will go away, and the separator will go away, and we will end up with this. If we had it the other way around, then we would still have the separator sitting on top of us, and that's not good. The downside is when I turn on the shroud, we do get a little bit of Z fighting there, which is kind of unfortunate. And it looks like, yes, I set up some struts because this is kind of wobbly at one point, and I set up some struts, and apparently I changed a fuel tank out after I did that. Yeah, I added a fuel tank in there, and I forgot to place my struts back again, so let's just do that real quick. This is a little bit fiddly because I want it to look right. So there's a problem there that my struts aren't being radial. So we'll do that. I think I'm going to attach the strut down here since I'm having to reattach it from scratch. So from there, and I can just attach it like this. Too bad there's nothing to snap to on this one. Oh, wait a minute. This old trick I used to use, I can try that, is that I could, in fact, snap it to the inside on the other side. Oh, snap it to the other side. So I can put it out here, like that. And when you do that, it snaps it back in to this. So that got it really nicely aligned. or I can do this. So we're going to put it at the same level, just like that. Boom. There we have it. Minimum length struts to keep our SRBs from wobbling about. Save. So there's quickly Concerned Tramp. I put in, let's see, 158 and 1972 and 1475 and 1533. I like to record the delta V in the comments up there because then I can just copy paste that around. So there's B01. Got everything we need. Now when we launch, it's going to wait until the appropriate time to launch. Let's take a look at that. Bring up the code editor. So a couple things. First off, it's a polar orbit, so we're going to want to launch azimuth that's north. We're going to go a little bit west, 10 degrees west-ish. That should be enough to cancel out our horizontal velocity because the sphere is going around and around to the east. So if we put ourselves to the west, it'll cancel out that velocity. That's a guess, minus 10. The key thing is to have it be within stretching distance. Here's our contract, which we set. It's huge. And our activation. So activation is where we extend the stuff. But we wanted to look at, not this part, we wanted to look at where we actually are waiting for the right time to get underway. So, phase match longitude of ascending node. So we know the longitude of the ascending node. Well, what does that mean? That's an angle between a specific vector called the solar prime vector. So the solar prime vector starts, the solar prime vector is a direction. It's an arbitrarily selected direction, and the equivalent in the real world is it points out somewhere in Aries. A specific place that astronomers picked at one point. In Kerbal Space Program, it points at a specific spot on the skybox, so it's always the same direction. And it's always perpendicular to up. So we take our solar prime vector is going to be, if I take it's mirrored, so left hand rule. You should see this as my left hand. If the solar prime vector is my z-axis here, which is pointing off to the right, no, it's easier to just explain it. So we've got our plane of the ecliptic, which is our zero plane for the entire universe. It's the y=0 plane, and everything happens pretty much in or near that plane. Kerbin itself is not appreciably tilted, so its north pole points upwards out of that plane. And when you want to measure a location within this spherical system, within the sky, you have a spherical coordinate system. So you start at this solar prime vector, and you count degrees moving east. And when you're either above or below your thing, that's your longitude of whatever it is, and then you go up or down. So the longitude of the ascending node is you start at the solar prime vector, and you rotate east until you're pointed out towards the ascending node of the destination. That's an angle. Well, so that tells us where it is, roughly, because we know what the solar prime vector is, we know where Kerbin is, we can draw that vector, we can draw the vector from Kerbin through us, we can look at the angle, and so on. So let's do that. In order to get the angle, though, we don't want to take the angle between two vectors, because then we won't know whether we're front or back. So we set up a vector called ship lonvec, which is we take the up vector, which is the vector from the middle of Kerbin through the ship, and we just cancel out any north or south of it. So if we're not exactly on the equator, this will take this vector, which may be up or down, and it'll make it absolutely flat along the plane of the ecliptic. Actually, it's all Kerbin's equatorial plane. And then we look at this. We say, well, what's the cosine of our longitude? It's the dot product of our longitude vector, which is, these guys have unit length, so it's the projection of our unit vector and our longitude in our ship lonvec direction along the solar prime vector. So if we are at 0, then it's going to project. It's going to be 1, and as we are further around the angle, as KSP moves further around, it's going to get smaller. And then the sine of our longitude. So we want to get that angle. The sine is going to be how far forward of it we are. Well, to get, again, if the orbital plane is this way, we're looking at from the top, and our prime vector is to the right, we want a vector that goes up. And using our left-handed rule, x, y, z. So z is pointing out. So z is the north from the body, because the body has no inclination. I need to consider adjusting this for bodies that have orbital tilt in the future. But we take the up vector, body north vector, cross this, so z cross x gives y. So here we go. We cross the solar prime vector with the body north vector. Hope I haven't got a sign error here, because this is working. This is working. So solar prime vector cross body north vector. So x, z should give minus y. Have I got that reversed? Oh, left-handed rule. Right. It's a left-handed system. So it goes the other way. So z cross x is y. I am confused. Don't take that as gospel. But do accept that for the moment, this appears to work. So we take our lonvec and we project it onto that perpendicular vector that gives us the sine of the angle. We use arctan 2 to go from the sine and the cosine to a angle, which can be plus or minus 180 degrees. Now, if we just said the ang between A and B, it would just give us a positive angle between 0 and 180. We need the sine, so we have to use arctan 2. UA is a support thing that says my argument is a angle in the number of degrees. Please return an unsigned angle in the range from 0 to 360. There's also an SA, which is minus 180 plus 180. Those are now in the standard library. We're done with them. Never have to think about them again. We'll just use them. So UA we will use to condition values where we want the result to be in 0 to 360. So that gives us back our ship's longitude relative to the solar prime vector. Well, we know our ship's longitude relative to the solar prime vector. We know where we want to launch, which is the target minus the lead. So we're going to launch when we're almost there. So we're going to take the match value and we're going to subtract a little bit from it. It's like 1 degree. If we just launched it exact, by the time we got up into orbit, Kerbin would have carried us on through. So we're going to give ourselves 1 degree. The other way of doing this would be to find out exactly when we're directly under it and launch a specific number of seconds before that. Either way would work, but whichever way we choose have to tune. I've decided to go for the 1 degree before. Bada boom. So delta ln is how many degrees we want to wait. We want to wait for Kerbal to rotate that many degrees. And Kerbal's rotation period is here, so we can take the change in the number of degrees, multiply it by degrees per second. Rotation period divided by 360. Rotation period is all the way around. Divided by 360, that's degrees per second. Seconds per degree. Multiply it by seconds per degree, so degrees times seconds per degree is seconds, so delta seconds. Okay. Remember, I'm reconstructing how this is working from the code because I wrote this yesterday. So we now have how long we should wait, how long we should be in pad hold so that when we launch, we'll be somewhere near the correct orbital plane. And if it's less than 11 seconds in the future, we're going to release ourselves from pad hold. Now remember, this code is going to get called over and over and over again. So eventually we will call this code when we are within 11 seconds of launch. At that point, we will release ourselves from pad hold and print some stuff out and go. If we've got more than 30 seconds to go, I am going to use warp 2, which is the time warp mechanism, to have KOS put us in time warp until we are at the 15 seconds before launch. That'll give us, a bit of overhead. Warp 2 is nice. It'll ramp your time warp factor up and back down, so when it's done, you're at about where you asked for. It returns immediately, and we return once. So then we come back, and a second later, we're going to call back, and we end up going back up to the top, grab everything, and basically, as long as we are in time warp, we're just going to call this back every second or so. If we're not, once rate gets down to 1 again, we are going to verify that time warp is settled. Now, it could very well be that settled will be, true the moment we get back to rate equals 1, but this is safe. So when we come out of time warp, we run all the calculations again. We might loop through this a couple of times to get down from 15 down to 10. Where we're done, it's 10, and we're ready to launch. And that's all the new code. And that's 25 minutes. That was more new code than I really wanted to have on a mission. But here we go. I wanted to get this done while we are here in the VAB, because as you see, when we roll it out to launch, it's immediately going to put us into time warp, so it can send things up. Now, maybe with all the new code, I won't have to talk so much during the actual flight. So let's launch. Okay, so there we are. Those messages going by. Let's bring up a console so we can see what those were. We had some debug prints in the pad hold code. So initially we needed to wait for 96 degrees of longitude, and when we came back we had 0.17 degrees left. And there's our launch. Now this is continuing to use the ascent code that was there from the last time. So when our apoapsis gets up to near our target, which is 80 kilometers, we're going to throttle way back. But it's going to continue to burn at a slow rate until we're out of the atmosphere to try to counteract the drag of the atmosphere. You'll see our apoapsis down here. If it's visible, we'll roll up to, 10 meters below, 5 meters below, 2 meters below, and so on, and we'll kind of hold. Bink, bink. So if we watch this from the map view, Now that we're in the map view, we can see here's the orbit we're trying to reach out here. And there's Mun. So it's a big orbit. We can also see, if I zoom in, that when it waited until the launch was in the right place, it really did nail it pretty much right on. So here's the center, and the center has continued moving, but here we are. And we are almost dead on that orbital plane. Right now this says that we are within 1 degree, so correcting our inclination will be very easy. This beats the heck flying out to the altitude on an orbit in the ecliptic and then trying to make a 90-degree turn in space, which you could only do if you're in a World War II biplane or you happen to have a handy black hole. Or a dark neutron star. Thank you, Larry Niven. Okay, so now we are coasting. Our apoapsis is at our parking orbit, which unnecessary precision, but a controller tends to nail the precision for you whether you like it or not. Notice our throttle backs off because we are trying to control our attitude while we're burning, and if our attitude drifts away from where we're supposed to be burning, it will drift off. Now with this configuration, I noticed during testing that on the long burn to get out to our outer orbit, I don't think our thrust vector is through the center of mass of our little satellite, because it periodically will go off center and have to be brought back in. Okay, shifting focus to Kerbin so I can center this up. Anyways, there I'm pushing the apoapsis out. So we have gone right through circularization, where we nailed it to within 125 meters and a final speed error of 1/10 of a meter per second about. And now we're pushing our apoapsis out. I'm trying to keep the sun behind Kerbin. Oh, let's go the other direction. There we go. Okay, and this will place our apoapsis midway between the apoapsis and periapsis of the target orbit. I adjusted that. I thought if I was putting up a real satellite, it might be kind of neat to match the period first, and then at some appropriate point in the orbit, burn to get the eccentricity correct. Now obviously if we have to start matching hyperbolic orbits, we'll have to do a special burn to match the periapsis of the hyperbolic orbit, and then burn like heck at the periapsis to try to get our correct hyperbolic velocity. Again, we'll do that when we get to it. So we are coasting out to our apoapsis, which is at 14 million meters. And our target orbit is from 14.4 to 13.6, so we're about halfway in between. Now, I've been doing a lot of time warping work here, especially during the launch. I didn't want to automatically warp during this ascent phase, but manually, if I reach up here and set the warp, I do have code that will say, oh, we're faster than warp factor 5, time warp 5, so we'll run it back to 0, and then we'll do a warp 2. And that saves us a lot of time sitting here looking at things. Okay, so now we are nearing our apoapsis, and we're just going to use the old stock standard unmodified circularization code that says whatever altitude we're at, burn to make us circular. And we are close to it. Not there yet. That's our time to apoapsis. think it starts, yeah, minus 30. So 30 seconds before apoapsis, the standard circularization script kicks in. And we just happen to have burned. Okay, we happen to have staged at the same time as our orbit happened to also intercept the moon. So that's what that weirdness was with the orbit in there. It was we actually had an intercept with Mun. The fact that it happened while we were staging means there's a good shot that our detritus that we just staged might be on the right trajectory to hit Mun. I don't know. So also during that, you'll notice that the contract went away, our reference orbit went away. Apparently, you don't have to be real precise about matching the reference orbit. So literally, we had a relative inclination of about a degree, which we're going to correct that. I mean, we still know what the orbit was, and the code is still sitting here, and it's still going to go correct it. But we didn't match our inclination closer than a degree. We didn't do anything to adjust our apoapsis and periapsis to be the correct distances, much less in the correct direction. I think they were approximately in the right direction. I didn't notice actually. But we got into the right orbital plane within a degree. We got into the right altitude, the right period, some band. I don't know what the actual conditions are for matching a contract. It'd be nice if I knew he'd match the contract and I could just, shut down this guy. But he's going to go ahead and try to match the inclination. Let's put him on a high time warp, which he will crank that down. So as we get closer to our correction point, it reduces the time warp factor. Down to 100. I'm tempted to put in some special code into the inclination matcher that if I push on the brakes, it says, oh, we're not going to bother with that. But that would just be a convenience for when we're doing it here. If I'm not recording or streaming or anything, I'll just sit here and wait. So that's what we'll do. So time warp down to 50x, 10x, 5x, and we have aligned for the burn, and it's going to correct us by about 1 degree. We probably won't even see it, but if I do this, we'll be able to hear it. So we're pointed off to the right. There it is. Blip. And we corrected. And now we have activated on station. And I think that's the attitude that I selected. And it has bipped out its little radar there. So now if we look, we do see that we have a radio connection to something. So there's our entire CurbNet network now. So apparently there are ground stations in several places on Kerbin. So we didn't have to set up a full ring of satellites to have connectivity. Yay! Let's take a look at this guy. High gain antenna. Currently idle. Aim camera at it. Okay, so that aimed my view. see. I can observe the mystery. Can I observe the mystery goo? Yes, I can. So mystery goo observation. I believe I have a contract in the contract house that says send back some science from orbit. So I am going to not do this until I've taken that contract. But I think I can observe the mystery goo and transmit the data and satisfy that contract. Let's try it. So from here, I want to go to the Space Center. This leaves the vessel in orbit. We now have a satellite in orbit, and its microcode is running, and it will always pick up at that stage where it is maintaining its orbital attitude. So we could write code in there to, for instance, keep something in Kerbal synchronous orbit. So somewhere here is, oh, it's not here anymore. There was a mission to bring science back from orbit. But you notice now we have a rescue mission. So that's going to be the next big thing I have to work on, is how to do a rendezvous with a vessel, not just getting into a specific orbit, but getting into the orbit and then matching with something else in that orbit, and then doing a real rendezvous, not just within the same orbit, but actually down to, under 100 meters, so we can jetpack back and forth. So we have some tourists here that want to do orbits, and we have a tourist that wants to do orbit and a rescue, and another satellite, equatorial high orbit. Anyway, just for fun, I'm going to go ahead and do that bit of science and send it back. Tracking station. So inside the tracking station, now that we have a couple of ships up there that are satellites, we can see we have our two satellites. There's no link between them because between them their radios aren't strong enough to talk to each other. But they do have links to the ground. Debris. What debris do we have? Oh, we've got some debris here. I've got this guy. Now he was the one that had a close pass to Mun at one point. And he's the one that actually has a close pass to Mun now. So I'm going to leave these just orbiting in space. And the last debris, this is actually debris on the ground. Let's recover it. So apparently he's going to have a close encounter with Mun, which is going to change his orbit slightly. We can watch that happen over time. So I have, apparently there's two different things I've got. One is a probe, and the other one is a relay. So the new satellite I put up is classified as a relay, probably because it has two antennas, and a probe only has one. That makes sense. Okay, so back out to our relay here. We're going to go grab the science and send it on in. So we booted up, and it greeted us, and it told us where it is, and it says it's in the station phase. And every 10 seconds while it's on station, it's going to verify that it's actually got itself pointed the right direction and got its antenna right. I'm tempted to adjust it at some point so that its preferred attitude is engine toward Kerbin, so that it will look like the antenna is pointed the right way. But for now, we'll observe the mystery goo. Oh, and we can't transmit it because we don't. Yeah, okay. We transmit it. There's no science there. Oh well. So we're not actually going to do that. Anyway, that's it for today. I will see you next time when we will start working on probably math to do the rendezvous.